Okay, so I will repeat again, please, because I was talking already. Okay, so this is the density of the states, and as I mentioned a moment ago, this density of state is telling you how many states there are per unit value of energy, right? So as here, remember this. Just I need you guys to remember this picture. So because you did this, the many potentials, and that's the reason why we have here the density of states. So it means that in these peaks, there are a very large amount of electronic states. Okay, here there are several electronic states. In this plot, here the dotted line is the Fermi level. The Fermi level is located by default, it is at the highest occupied state, the electronic state here, right? And as you can see, above the Fermi level, there is no states. So we call this a band gap. Okay. Below the Fermi level, we consider the valence band. Here's the valence band, right? There should be more states on the left, but here, since we were not using the core electrons, that's just we don't have them. So this is only represents the valence electron. How many electrons? How many electrons has the system? How many electrons? No. How many electrons? You can check either in the postcard file. Remember, in the postcard file, we're using 4 electrons for each silicon. So there are 8 electrons, right? So in total, there are 8 electrons, right? But in the outcard file, also, you will find this. If you're wondering how many electrons, you can come here and you have this, right? Sorry. This. You see? So there are 8. So from the outer file, you can have also this information. It has these 8 electrons, right? Well, we have 8 electrons. Why? Because each atom provides with 4 electrons, right? So here, I repeat again, the left is the valence band, on the right is the conduction band, okay? Or the empty states. And here's the band, right? Okay, so any question here, please, somebody. Someone needed to explain again this kind of the density of states. No, this up here, please. Angel, you promised me that you are not going to forget about the density of states. Just remember this picture, right? Remember the density of states. You see, is the number of electronic levels in a delta E. The higher, see, this is almost continuous, but we can still distinguish this kind. Okay, so. Let's continue then. Now let's explore a little bit more this, okay? So please plot, let's take this. Let's copy this, please. And let's make a zoom around this region. So we're going to do plot range between this 5, 6.5. I want to zoom this region here, all this region here. I want to see what is in this region here, okay? So as is, I'm going to zoom this, and this I'm going to put 0.2, 0.0. There it is. Okay? So, as you can see, I repeat again here, the density states above the Fermi level is 0, right? And this we call the band gap. Okay, so this system we call is insulator, right? So there are insulator or metallic systems, right? In this case, since the fuse, you can even check how much will be the Fermi level. Let's say, for instance, you want to check the Fermi level, you can check this. Sorry, the band gap. So we can estimate very quickly doing this. You select the figure, and you press point, and a cross will appear, and you can check this point, right? So I'm going to copy this point here. So will be the EF. So my band gap would be around 0.5 electron. How I did it, please, I just click on the figure. I repeat again, please. Just to check very quickly, right? You press click on the figure. They appear this kind of orange frame, And after you press point, a cross will appear. And after you go to the lowest part here. You point here at this point here. And after you do click here, Control C, Control V, you're going to have this. This is the coordinate. I need only the X value, so that's the reason I subtract from the F and I have this separate. So in this case, the band gap of this system is predicted to be 7.5. Okay. This we call, if there is a band gap, we call the system is insulator. But in among the insulators, we also like to distinguish as, for instance, if the band gap is less than 2 electron volts, we call semiconductor. So this system is a semiconductor. Experimentally, the band gap of silicon is 1.1 electron volts. So, and we get 0.5. So that is typical in DFT. We always, the standard DFT, we will do any calculation with DFT, with the standard functions, let's say, you always are going to get a band gap that is smaller than the experimental one. Okay, so that is a limitation of DFT because DFT is based only on the electronic density. So it means only on occupied states. That's the reason why, in principle, we shouldn't take care. We shouldn't consider too seriously these empty states, but by experience, by using this DFT, it looks like this, and anyhow, these empty states, these are good description of the empty states in the real okay. Anyways, there is a better calculation, right? So you can improve this using hybrid functions, for instance, and you can correct this one gap and the nature of this electronics. Okay. Questions here, please. Yes, thank you. Very good. Yes. I forgot to mention the density of states, this kind of states, you know, with this, as I mentioned, has a lot of information. You can process this information to, for instance, to simulate the XPS or the UPS. In this case, XPS, is more used for the core electrons, but XPS, you can have also some information about the valence band, right? The valence electrons. Of course, it depends on the resolution of your XPS, but it's possible to get in. On surfaces, the density of states can be related with the UPS, the ultraviolet photoelectric spectroscopy. So you can post-processing and you can get this. Okay. So it means that the peaks are related with some peaks that you will see in some spectroscopies. That's the reason why in a moment we're going to decompose this to see the nature of the peaks so you can explain in experiments. It's very handy, the experiments. And I repeat again, density of the states only appears in solids, in periodic system. Remember this. This is because you have a bands here, but here, not. In molecules, clusters, no, you cannot talk about the density of states because you don't have a periodicity. You are not applying block function. So that's the reason why it's not possible to talk about density of states in finite systems. In 0D systems like molecules, clusters, it's not possible to apply these densities. It's not possible to define densities. Okay, only in periodic systems. Okay, remember this. Please write down because you will be asked this in your mid-term challenge course. Questions here, please. Wanda, any question, please? Anton, somebody want me to repeat again these explanations? No? Santiago? Okay, so let's continue now. Let's understand this. Ángel, if you integrate this, Ángel, if you have this is the density states per electron. If you integrate this from here to here, what should have? For instance, you have a density. If you integrate density on the space, what you will have? or if you have this, if you integrate on the energy, what you should have?
You think that is related with electron?
Yes. So if you integrate three years, what you should have? The occupied states.
The one half of probably no one half.
One part, one part.
I think that is related with probability to find an electron in not. Or
Not necessarily, but it is related with electrons. Then if you integrate the density states from here to here, what you should have? Santiago? Here to here.
you have a number of electrons.
Correct. So we should have the total number of electron systems. So let's check this, okay? So let's do the interpolation. First of all, we have to do the interpolation. So I'm going to put here. Interpolate. I'm going to put like this. Interpolation of what? Of dots. Okay. So I'm going to do the interpolation of this, you see, because otherwise I cannot do any integration. And after that, I'm going to do integration. So I'm going to integrate, right? This in next, comma, x going from minus, you see here, minus 8.2 to EF. So I'm going to integrate I'm going to integrate this from this minus 8.2 from here till EF. So if you get this, I should have, so this, it is around the value of, right, so it's around 8.05, you see? I don't get 8 because the resolution by this state is not the best, so I could increase the resolution of the states, you know, that it's okay. So for our purposes, it will be fine. As you can see, if you integrate the density of state from minus infinity to the Fermi level, you should have the total number of electrons. In this case, we only have 8 because we have only 8 electrons in the system. We are using the only 8 valence. Okay. Let's continue, please. Okay, so I'm going to below. We are going to analyze the partial density of states. Okay. So, first of all, from the help, okay, so I'm going to open the wiki, the vast wiki, this here. If you open the vast wiki and you put DOSCAR, you're going to have the information of what is this DOSCAR file. As you can see, the arrangement of the DOSCAR file of the data goes like this, you see? Goes like energy, px, like this, etc., etc. See? So this is as I mentioned before, the arrangement of this. We did arrangement. Below is the arrangement of the data. Okay, here it is. So I'm going to open the density of states here, you see. So here is, as I mentioned, this is the total density of states, and this is the partial density of states. This is related with the first atom, as you can see. So this is the energy, as you see, energy S. This is S, Py, Pc, Px, and the D. Okay, so that is the arrangement. So what we are going to do is now is to create a partial density of states by channels. So I want to do first of all, I want to check the S contribution, the P contribution, and D contribution. So let's do this, okay? So first of all, I have to extract the data. So I'm going to put those one. So it will be for the atom one will be input, right? You see, this line here is 7 plus 300 plus, right? Plus 2, right? Because I went from here to here, from this line. So remember, this is 7 plus 300 plus 1, so plus 2. So I will go like this. 7 plus 300 plus 2 until the same value, you see, plus 300. See, this is the range, okay? Why? Because we know that from here till the next, till here, there are 300 values still here, right? And that's it. Okay, so we have this. After that, I'm going to do this, okay? Those two, I'm going to take the data from those two will be exactly from here. I'm going, you see, I'm going to copy this, paste here, plus 2, see, colon, and I copy and paste this, plus 300. That's it. Okay. So this is basically what I'm doing is taking, for the those one, I'm taking the values from this line to this line, right? And the second set will be from this value till the last part, till here. Okay, so we have this. Shift enter. Now I have those ones. So let's check it chat. Those one, I have this, you see? And those two, we have this. Okay. Now I'm going to get the those all. The those all will be equal to this, right? So it will be like this. Those one plus those two. But since I'm adding the two blocks, I'm going to repeat this is this value twice. So that's the reason why I'm going to do this. Map. I'm going to divide only the first value by 2, followed by how many values. So there are, in each line, there are how many values? Let's see, it is here, you see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values. There are 10 values in that one. So that's the reason I put this 10 values. 1, 2, 3, 7, 8, 9, 10 values. So there are here 9 ones and only one. Okay, that's it. So I divide like this and comma, stack, and there it is. Okay, so let me see those all one. You should have something like that, you see? So it should have the same energy because the energy values is the same for both blocks. That's the reason I'm going to do this. And that's it. Okay, I'm going to pause here for a moment till everyone is here. Okay, so I'm going to check again. Please tell you again. I'm going to define these functions that will extract information from the data we computed. And here, for instance, we sum all the values from the 2 to the all these. If I sum this, it is the total density state. That is what I call F total. But also the S is just to consider this value and this value here, the energy, and the first value here. That is the S channel, the projection of density states to to the S orbitals. The P will be this value and the sum of this, the total P, right? And the total D will be this value and the sum of all these 5. You see? We have this. That's the reason from 6 to 10. Also, I extract information PY channel, so it will be only this one, right? This is PY. PC will be this one, so that's the reason I put 4, and that's the reason I put 5. And that's it. Okay. So now let's check if it's working, right? So I'm going to check if it's working. So I'm going to put like this. Those all. That is the data I'm going to to track information. I mean, I'm going to put the F total. right? And after I'm going to put list plot. See it works, right? This, comma, see? If I do this, look this, I have this. Just I'm checking if it's running. Okay, just you can check there if you run. So I repeat again here. What is doing this, just to explain again this function total is taking the first value of each row on the data and is adding all the remaining values. The remaining values is the projection of density space in S, E, and D. So the reason we have this. And that's I call it total, right? But also we can check this, right? We can check the S. Let's check the S. I'm going to copy this. Let's copy this, paste it here, and just put PS. I'm going to check that's only the S. There it is, the S. Let's check the peak, please. The peak. You see? As you can see there, this is very important because you want to understand the composition of the density of states. I can use this, right? So just in case, let me see if there's the D. If there is D, because we have D channel, but in D channel is practically zero. There is no contribution of D states on the okay. So now we're ready to plot everything together and to produce this figure that is here. Please, let's reproduce this figure here. So we're able to reproduce this figure. Now let's reproduce this figure here. Let's do it. So how to do this? We're going to do this. I'm going to combine those all, right, with F total, comma, those all, F. I'm going to start with Fs, comma, with Fp. That's it, right? Because there is no contribution done. And this, I'm going to do this. List plot, okay, hashtag, comma, I'm going to put like this, see? Don't forget to put here the and, okay, don't forget, do this, I close this, and, okay? And now let's put this, the options. Net, true, comma, grid lines, I'm going to put the same as before, EF, comma, none, filling, I'm going to put like this, two axis, two axis. Prime true, prime level, energy, dV, and in Y is the P2. I'm going to put in arbitrary units, R units. Okay. Plot range O. Plot legends. We're going to put plot legends. Okay. I'm going to put like this, placed. Total, comma. First is 3, remember the channel is 3S and the other is 3P. Right? Comma. Scale, just to get the same, is 0.75. That is to locate this in that position. Image size 800. Access false. Grid lines styles. Absolute thickness. Okay. Plot style will be like this. Absolute thickness 0.8. Absolute thickness 0.8. I'm going to put the S states in blue, okay, and the P states in red. And finally, there's this time. Size 18. And let me see if it looks. Hopefully, yes. There it is. Okay, so I'm going to pause this here. Okay, I'm coming to you. First of all, this is the partial density space. Okay, to analyze this, right? This is it helps a lot because the black line is the total density space. So you sum all the states and you get the total density space. You see here, the black line. So it means that the nature of this band, in this, for instance, always you analyze around the Fermi level, very important. You know, around the Fermi level, the electrons are very active. That's the reason we like to see what is the nature of the composition of the density of states around the Fermi level. As you can see, in the upper part of the valence band, the nature of this the density of the states is due to the free p electrons with little contribution of s electrons. But if you go to the lower part of the valence band, it is the character is 3s. See? 3s. This is very important for instance, for people who are doing spectroscopies, because you can explain them why you get a certain signal, right? On the conduction band, it means that this is also very important, you know, the lower part of the conduction band, because if you excite one electron, you know what will be the character of the. In this case, the character of the electron that is leaving, if it's excited, it will be a contribution of S and P. There is no weakness. More or less. Okay. Okay, so some student asked me, how do I know the channels are here, by the way. If you see the density of states, the P dot or the dot scar, you are going to see this. So you know that first of all, it is S, this is P, these are D. So here only has contribution on the density of states is projected to S, P, and D. But it might happen also you have F electrons. So you're going to find 7 more values F electrons. Okay, so you can see from this. That's the reason before you plot this, you have to check if you have more data here. So if you have more data here, you have to correct here. No, you have to add here. You know, there are two parts you have to correct. Will be here. This part, please. So will be so from 2 to 17, because will be 7 more states for the G for F states, right? And here you have to add F that will be from 11 till 17. That will be the okay. Questions, please. Somebody. Questions. Don't need to repeat any part, please. Questions in here, please. Is that clear? This. So this is very important when we compute the density of the states. We also try to get the composition. So at least in what channels, right? So in this case, I repeat again, it is the main character of the valence band is due to the 3p electrons. See. Questions in here, please. Questions. Questions. Okay. So just to, I'm going to pause here. Okay, now we are going to plot. This is not in the manual, but it's just for your information. So I'm going to plot also the composition of the p channels. So I'm going to check px, py, and pz. So I'm going to put those all px, py, px. Sorry, those all px, py, and pz. Okay, so I'm going to plot only px, py, and pc to see what happened. Okay, so I have three. In this case, I have three composes, three channels. So in this case, I have to put this will be px, py, py, and pc. See, this is the same. And now I want to do plot the style. I'm going to put the green. I'm going to put like this: green for px, blue for py, and red for pz. And that's it, right? So I'm going to do this. Let me see what happened like this. There it is, as you can see. So basically, what is this? It means that the px, py, and pc contribute equally in this. It's a cubic system by symmetry, right? So px, py, and pc are equivalent. That's the reason we have exactly the same position in the three channels. Okay. Okay. I'm going to pause here, please. Okay, so now if we follow the instructions, we're going to plot the band structure here. We're going to reproduce this. Okay, so for this, we're going to use this notebook, please. This is something that I shared already, this one, okay? So this is one structure. So it is here, is telling you the some data that you have to put here. So I'm going to use this, okay? So I'm going to copy this, and I'm going to put in my notebook here, okay? So let's rename this, please. Let's put one structure from procar out along. Okay, I'm going to raise this along the path L gamma L gamma X K gamma. This will be that is the path I'm going to follow. And as you can see here, I'm going to copy this just in case to have this. Okay, so here is the one we used yesterday. So I'm going to copy this just to have it as a. This is from the, remember, this is from the SIG path, right? So I'm going to put format, cell, I think, cell, format at the center. See? So this is there it is the path we are going to use, okay? Okay, and here let's put this here, put your directory where the data here. So let's put this directory, please. Directory, we put it here where it is here. So here's the data of the file that we're going to use. It's here. I'm going to put the spaces here, please. In my case, it's here. Okay. Please do not touch this. This is just to extract information from the procar. So we're going to use the procar opt. So I will explain what is exactly this we're going to do from this file. This, where is this? Here, this, where is this? So when you computed, you got this procar opt, as you can see from here. See? So in this case, we're going to, as you can see, we're going to use this data for we need this and we need the energy. You see? This is the data I need. You see? So based on this figure, so here. So basically what I'm going to do is this, right? So if you have this, I'm going to do from, for instance, I will start from L to gamma. Just I will explain this part. Okay. So what I'm going to do is to divide, in fact, in this procar file, it divides these segments in certain delta K. So you see K.1, K.2, where is K.2? Here. K.2, no? So you see, there is a small segment from here to here, so it computes the energy in this point, and after in this point here, I'm going to zoom here, in this point here, in this point here. So there are 30 sections here in this, what it divides the program to compute the energies, right? So that's it. So I'm going to, so basically for in each direction here, this in each direction here is divided by segments and computed energy in these points. It's in a 3D, right? Because it goes through next goes to K and so on. So the point is that we have to linearize this because it's in a 3D, space. So we're going to linearize and put this only one dimension along the K vectors, and the rest, and the y direction will be the energies, right? So this notebook is telling you is doing this for you. Okay. The only thing is that we have to check what is the Fermi level. So let's take the Fermi level from this outcome file, from this guy, right? So we already compute this EF. We have this EF, right? EF is this, right? It's already taken, but anyways, EF is this. So we have to copy and paste it here. You see? Okay. Because we already take this, but I put this because if you want to run, you can run independently if you run the upper part of the lower. So I put this redundant information. The rest is exactly the same. Okay. No need to change and so on. Okay. So this is the bands. In this case, Santiago, you can put just from 1 to 8 because you have 16. So just put from 1 to 8 and it will be fine. Okay. And the rest, let's see, it works, right? So let's run it this. So I'm going to collapse this and let's run it. Okay, so let me see this. And there it is. There is the bands. Okay. So I'm going to pause here till everyone gets the same. Just you have to change the path. I repeat again, please. You have to change, you have to give only this information, please. Put the path where you are working this section and the Fermi level. Put the value that we computed, the EF. Just put EF that we computed already, EF equal to this, and that's it. And you're going to have this path. Okay, for the students who doesn't have Windows or doesn't have Linux or is running this notebook in Windows, you have to be careful. You have to run this in a terminal. You see, I put all these commands in order. First of all, shift enter, 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 and the last one, please. So the last one here, please copy this. Do the following, please. Be careful. Don't do this. Do just change this, please. Put this, please. Instead of this, change to this. See? You put this, not you erase this because in Mathematica to run this command in Linux, you have to replace that symbol by this. But after this, you should have this. See? You change to this. And that's it. That's it. After this, please just comment this. Please, you just select this and comment and just run it. Now run it because you have everything will be like this. Okay? Let me know if run. Okay. So the band structure give me also very useful information. First thing is that what is the use of the band structure is very important because using what is this? Transport theory, you can predict the conductivity of this material. So the conductivity of any material depends on the bands, you see? So you can do a post-processing and you can compute the conductivity. Second thing is here, right? So you have this, see, this a bit. Oh. Okay. Okay. First, one thing is important here. You see, the highest occupied electronic state is here. See? So the highest occupied state is here, you see. Right? And I shift, as you can see in this plot, I shift E minus EF. So this zero is at the Fermi level. It's just like convention, remember, because the Fermi level could be between this and this value, so it will be in this region, right? Because you can tune it at the Fermi level just by doping. But in VASP or in the condensed matter community community, we like to put the Fermi level at the maximum occupied state, right? One thing is that if we want to move one electron to the lowest conduction band, lowest part of the conduction band, the electron can just move from here to here. So this is the lowest one. So as you can see, the wave vector of that state is not the same. So it changed. So that is not, so by conservation of momentum, remember this axis, the momentum is related the k vector here is related with momentum, right? That's the reason we sometimes refer to momentum. As you can see, it's not the same. Therefore, if the electron wants to go from here to here, it has to involve something else to conserve the momentum. What is that? A phonon. So electron can go from here to here if and only if involves some phonon of the system. So what does it mean? First of all, if the electron wants to go to here will involve a phonon, it means that the system will start to produce some heat. Okay. So we call this, in this case, what the momentum of this state and this state is not the same, we call an indirect band gap. Right? Direct band gap will be this case, right? We're going to have direct band gap if we have this case. This. So, we can, yeah, right. Direct band gap will be something like this. You have this for a mechanical. You see, that is the energy, and this is the K space. You see, that in this case will be a direct band gap. So for photovoltaic applications, this is the circle, right? Because we want a system that is able to excite electrons to the conduction band, but with no involvement of phonons. So this is, if you want to apply material for photovoltaic applications, this is not the best, right? Because this will produce some heat by default, but this not. But anyways, if you're going to see in real systems, many real systems have this direct band gap, and they still heat up, is because the system itself could have defects, has many boundaries and so on. That's the reason why it's not a perfect system. That's the reason we produce some heat, because there is this kind of defects. But in any case, this is an indirect band gap, right? And that's the reason why to go electron, we want to be excited from here to here, have to involve a phone, right? And that is silicon. Nonetheless, silicon is the most, so far I think is the most material applied for this kind of photovoltaic applications, right? Why? The reason is because the industry is right now is very stable. It's very easy to get very pure samples of silicon, because of the industry, silicon industry. And that's the reason why it's cheaper to produce this rather than, for instance, perovskites, that is the best so far, but it's expensive. The reason why. Okay. What else? About the dispersion, right? You see, the higher is the dispersion, right? The more delocalized are they. So if we have a flat band, let's suppose that we have here a flat band, So this band, it means that the electron is completely localized in some part of the crystal. Okay? Meanwhile, I dispersion means the electrons are free light, so it means like they try to be free. Now remember, this is in certain directions, right? So as you can see, because this system is a crystal, so electrons can move. The movement of electrons in certain directions are not the same in all directions. So if it is anisotropic behavior, and that is the reason when we compute the conductivity in fact is a tensor, right? The tensor of the electrons. Okay. Question to here, please. This L, gamma, X, K, and gamma, yeah, are we call this we call this the high symmetry points. Okay, so the high symmetry points. And here you see here this, so from here and then so from here you see we started from L to so you see, when I go to, I started from L to gamma, and I just divided in some sections, and I compute the energy into that one. See, that is what we did. And after that, we go from L to K, and also we divide in several sections, and we compute the energies. That is what we're doing. We're plotting this direction versus the end. Of course, the dispersion will be different depending on what direction we balance. Okay, that's the reason we mentioned the resistivity. You can apply a transport theory to predict what will be the resistivity of these materials, and of course resistivity depends how you apply the voltage, the direction you apply the voltage to get the current, and this is reflected in this constant. Okay, so this is one application. Just in case somebody asks, what is the use of the band structure? Is one is that, right? There are many other applications. Anthony, have any questions? Okay, let me check what else. Let me see this, and I think we have this, the Fermi level. I think I covered everything that I needed here on this. Okay, so now what remains is to compute. So to compute the band gap in the most exact way is to compute the bands. So now I'm going to isolate this band from this band to see what is the distance and energy from this point to this point. Let's do this, okay, please. So how to do this? So it's very easy. So I know there is by the way, how many electrons are occupying these bands? 8 electrons. Here we need 8 electrons, just in case. Okay. So let's compute, right? So let's do this, please. So I know there is 1, 2, 3. You see, there is 1, 2, 3, 4. This is a 4 band. Let me check this. So I'm going to put like this. B, C, 4. And the 5th electron is the upper one. 5. List plot. Hashtag. You see, we have this. So as you can see, this is 0. So this is the highest part of the band, and this is the valence band, the highest occupied band, and the lowest unoccupied band. Okay, so we have this. So I'm going to put like this. Int. And I'm going to interpolate the VD5, the band 5, right? I'm going to interpolate this. Why? Because I want to see what value is the minimum here. And I'm going to interpolate the 4 band. Because I want to check the high. Anyways, I know where is the highest is here, right? So anyways, below the highest. Okay. So I'm going to check what is the, let me see, find minimum of this. I want to check what is the minimum this of x, comma x. See? So the minimum is at in x in the x is 1.45. So here, somewhere here, but the value is 0.55. Therefore, you see, Since I know the maximum is in zero, you see the maximum here, this value is zero, the maximum of this band. So basically I can say that the band gap is around 0.56. In fact, we call the we call this the fundamental band gap is around the 5 electron volts. And it is indirect. You see, that is the most accurate way to get the band. Again, see? Well, it was redundant to do the interpretation of the band for because I know the maximum should be at zero. That's the reason why I should just consider the minimum of the conduction band. And with this, we can put the same band. And it's in there. Right? Okay. Questions in here, please, somebody? Questions? Questions? Now let's finish with this, please. We're going to finish with the visualization. I'm going to put a subsection called visualization of CHC car dot VASP. I'm going to put this as subsection, please. Okay, so please, in this case, we're going to plot, just follow me, my instructions, please. In Vesta, open this CHC car here. You see, you can open with Vesta. Open with Vesta, please. There it is. Okay. Now what we're going to do is, please, I don't want to show sections, right? And I'm going to change this to, let me see, where is my manual here? The value of 0.06. Let's change this here. You go to properties, please. Anyways, I'm recording. ISO surfaces. Click here and put here 0.06 to have the same, just because to compare with this. Okay, you see? So this is the ISO surface of this electronic density of the valence electron space. And now we're going to do boundary, and we're going to do three. I think it's 3 by 3 by 3, right? 3 by 3 by 3. 3, 3, 3. There it is. See? So besides, I'm going to put this view, and you put this, sorry, in where is in perspective. So will be this better. There it is, the electronic density. Okay, so as you can see, the electronic density in this system is of the valence electrons is in between the atoms, you see? So this is a clear indication of the covalent bonding. It's a typical covalent bonding, okay? So I'm going to create a file, export raster image, please. You can put export raster image, and you can put this here, right? So I'm going to put this, let's say I'm going to save it as a PNG, by the way. I'm going to put the one, only one, because I'm going to do second figure will be this. Save. I like to put the background transparent and leave it like this. Okay. Okay, so this is electronic. Now I'm going to generate this image, please. This here. So I'm going to do this. So if you like, you can put this here. So I'm going to put inside of mathematics, I'm going to put this image here. So this is electronic density. See? Now I'm going to make a cross section with a plane, please. So you come here, edit, lattice planes, and what the plane it suggests will be 1, 0, minus 1. 1, 0, minus 1. What is this? 1, 0, edit, planes, and you put this new here, and here you put 1, 0, minus 1. And the origin put please 0 here. Okay, there it is. Please,
Uncheck so isosurfaces, and you are having here the electronic density, the cross section of the electronic density. Please save it. Fine. Export raster image. I'm going to save like CP2, the second. I'm going to leave with transparent. Okay. Okay. So as you can see here, just to conclude this session,
As you can see, I did a cross section of the electronic density, and look here, very clear. The electronic density in between silicon atoms, the maximum is in between them. So this is a typical covalent bonding, right? Let's say the most covalent material we know in nature probably it is diamond, right? But silicon has exactly the same symmetry, same structure, but it's a little bit weaker. But anyways, we have also covalent bond. Okay. So save it, please, and you can put this in I can pass this to my Mathematica notebook. So here, and I can put this just to have it this together. So that's it. We have both. Okay. And we have generated this. Okay, I'm going to